Hello, my name is Narses Begian. I'm head of data science at Raiffeisen Bank CIB, and today at Advanced A/B Testing section we are going to discuss Advanced A/B Testing. We will talk about picking at A/B tests and how we could solve this problem. I will tell you about statistics behind it and the way how you will solve it. Let's start with statistics. In A/B testing and online experimenting, everything is based on statistical tests and hypothesis testing. The null hypothesis says that effect, which is the difference in average of two metrics, does not exist. And the alternative hypothesis says that the effect exists. It could be small or big, positive or negative, but it exists. So in this slide you could see a two-way to write down the null and alternative hypothesis. I propose to remember the second one and move on. I want to discuss with you how to conduct an A/B testing in fixed horizon setup. We could divide all A/B testing process in three parts. The first one, we calculating our sample size. The second one, we are waiting A/B test to end, and after we got our observations, we calculate p-values, this magical number which tells us if we should reject or not reject our null hypothesis. But what is p-value? If we are talking with a person who doesn't know statistics very good, he will say that the smaller p-value, the better it is for us. He will be right, but as far as we are on advanced A/B testing section, I want you to provide some mathematics behind it. And this magical value, which is called p-value, could be defined in two ways. The first one is classical definition from the Wikipedia, and it says that p-value is the probability of obtaining the same statistics or even more critical one if the null hypothesis is true, and alternative definitions tells us that p-value is the smallest alpha, which is type 1 error rate. And if we want our definitions to work, we should know that there is such a thing as valid p-values. What does it mean? Valid p-values are p-values that have a super uniform distribution. In fact, this is not very popular definition when we are talking about super uniform distribution. So let's understand what does it mean practically. What does it mean that our p-values have super uniform distribution under null hypothesis? And it could mean two things. The first one is that our distribution is right skewed, and the second one is that our distribution is uniform. So when you conduct 1,000 of AA tests, you should see the distribution that is either right skewed or uniform. And let's get back to our p-values and statistical tests and look more precisely at our second definition. We see that there is some decision threshold, K alpha. And I want to show you how does this threshold looks like in real A/B testing setup. And here I want to show you how this decision boundary works, how it looks like. We see that there are two black lines which represent our fixed horizon decision boundary. The red line, which shows the effect by we obtain some number of observations. And if we look precisely, we will see that sometimes our effect crosses our decision boundary. And if we pick it this time, the test will say that the effect exists, even if we see that in the end our A/B test showed us that the null hypothesis is true. So why our statistics cross the decision boundary several times? Why does it happen? There is such thing as law of iterated logarithm that says that under null hypothesis, with probability 1, our statistic or our effect will cross the decision boundary because it's proportional to square of log n divided of n, which is asymptotically bigger than 1 divided square of n. And what does this mean to us? What should we know about this? And I think that we should understand that we will eventually exceed this decision threshold, and it will lead to 100% type 1 error rate. And someone could say, sorry, Narses, do you really want to say that we should conduct A/B test with infinite sample size? And he will be correct. In practice, when we are fixing the number of observation to 10,000 and we continuously monitoring it and we stop the test the first time we see the effect exist, it will lead us to 50% type 1 error rate, which is very bad. Imagine that in your company you will come to your supervisor and say to him that the effect exists, that you see the real money in the A/B test when it doesn't exist. I think it will be very, very bad to you and your company, because it could lead to the wrong decisions, and in the end you could be fired. We don't want that, so there are at least 4 ways how to handle this problem, and I think they're very interesting, and let's go through them. The first one is setting alpha at a very low level, but it will result in very small power of your test. So you will not detect the effect when it exists. The second and the third way to handle this are very similar. It's using Bayesian A/B testing and multi-armed bandits, but we're not going to discuss them today because there are a lot of materials which will show us how to deal with them. Today I want to tell you about sequential testing. It's a very popular way in some companies how to continuously monitor A/B testing without inflating type 1 error rate. Actually, sequential tests in statistics is a family of decision rules which tells us when to stop the test. And it parameterizes by 2 things. The first one is t, it's the sample size when the test is ended. And the second one is delta, which is binary valued variable that takes value of 1 when null hypothesis is rejected and 0 otherwise. And so we could reformulate our valid p-value calculation process in the following way. We will say that it is the smallest alpha when our sample size t of alpha is smaller than n and delta is 1. I think that it's pretty hard to understand, but do this kind of decision rules, t and delta, even exist? And this is a question I want to answer. And they do exist. One of these tests is called mixture sequential probability ratio test, first introduced by Herbert Robbins in 1975. He proposed a way to calculate a new statistics using a likelihood probability ratio test with some prior distribution on the test effect. Given this statistic, we could easily calculate our decision rules and after that decide to stop or not to stop the test. And you could just say, wait, what happened? What did you just tell us? We just observed simple things, and let's go through them one by one. We defined some statistics, some value that we could recalculate once we got a new observation. How can we do that? So we upgraded a likelihood probability ratio test by thinking Bayesian. We added a prior distribution on the effect and moved to some probability mixture of probability distributions instead of just looking at and using simple likelihood probability ratio testing. The third thing that we did is we defined a decision rule for stopping the test. We also could define how to calculate p-value for valid p-value process, and it simply is 1 divided by statistics lambda. And actually our statistics lambda, if we are talking about some intuition there, represents the evidence against null hypothesis in favor of mixture of alternative hypotheses. And if we accumulated enough evidence, I think it means that we could reject null hypothesis and say that the effect exists. And the last question you probably want to ask me is how to find likelihood function and prior distribution. And the answer is simple. You should use your historical data and find such distributions that fit your data best. And let's hear some story from galaxy far, far away. There is some analytic which works in a big company, and his supervisor, let's call him manager, and the analytics comes to his manager and say, "Hi, I saw you just assigned a task to me. You want to conduct an A/B test, and I should calculate a sample size in advance. Could you please answer some questions in order for me to finish this task?" Manager says, "Yeah, okay." Analytics say, "Do you know something about expected effect in the test? Did you do some sort of calculations?" And his supervisor says, "Yeah, maybe from 1 to 3% in conversion rate." And analytics says, "Thank you." Why is he so sad? Because to detect an effect of size delta takes a run length proportional to 1 divided by delta squared. It means that when we are talking about effect from 1 to 3% in conversion rate, the run length could result in from 4 to 9 times longer than it should be. When we discussed this fact, I propose you to move on and discuss the result of performance of MSPRT. There are 3 cases: when we know the exact effect, which is never; when we are mistaken in our effect size by 30%, it will lead to 20% longer runtime compared to fixed horizon testing; and when we are mistaken by 50%, it shows us that we could be 2 times faster. What does it mean? You could say, "Sorry nurses, but you proposed us a way to make our experiment faster and continuously monitoring it." They actually say yes, and I just show you how we could do this, because in my experience I never seen an A/B test when we knew the exact effect before the A/B test. And when we are talking that the effect could vary from 1 to 3%, it means that we are mistaken by maybe 200% or 300%, and the MSPRT will work better in this case. So MSPRT not only gives us an opportunity to continuously monitor our test, but also not to calculate the sample size before the A/B test. And actually this shows us that we are robust not to knowing the effect size, and this results in shorter expected run length. Thank you. I hope this was interesting for you and you understand how to use MSPRT in your testing, and you will use it.